one of these things you can pick out as being the limiting reactant because it will limit the amount of pancakes that you're able to produce. Okay, so which one is going to be the limiting, just looking at that, which one is going to be the limiting reactant? Is it going to be the flour? If I have 3 cups of flour, that gives me 15 pancakes. Yeah, that produces the lowest amount of products, right? The 15 pancakes. So this guy right here is the limiting reactant. And that's all the limiting reactant really is. Right? So the flour is, okay, you can only get 15 pancakes. So this concept of limiting reactant, right, which is that guy up there, right, is simply the reactant that makes the least amount of the product, okay? And note also that it is also sometimes called the limiting reagent. Reagent is an older term, okay? So reactant is the same thing as reagent, okay? Now there is another concept called the theoretical yield, okay? The theoretical yield, it's the amount of product made with the limiting reactant, okay? So what is going to, in my pancake example, what is going to be my theoretical yield? Which one is going to be my theoretical yield?
15 pancakes.
15 pancakes. Right? There you go. This guy right here is my theoretical yield. Once again, all right, let's say what that is. You can even write this down. Well, I don't have enough space right now, but the theoretical yield is the amount of product made with the limiting reactant. That's all it is. Okay? So say instead of making 15 pancakes, we burn 3 of them. See, I told you I was getting to burning the pancakes, right? So it's not such a boring example. Let's say if in the real world, right, I'm frying these things up. I had all the things together that I needed. I had the baking powder, I had the flour, I had the eggs and everything. But I screwed up in the process, and I burned 3 of them. Okay? So originally I was supposed to make 15 pancakes. Remember, that's the theoretical yield, is the 15 pancakes. But in reality, what happened was I burned 3, right? Because I didn't use enough oil in the pan or something. So how many pancakes did I get? I only got 12 out of that, right? And 15 minus 3 is 12. So this introduces what percentage yield is, okay? Percentage yield is the following, okay? It is the actual yield divided by the theoretical yield. Theoretical. Times 100 to give you percent, okay? So in my example where I burned, let's say if I burned 4 of them, well, no, 3 of them. If I burned 3 of them, then I would have how many pancakes? I would have 12 pancakes, right? Divided by 15 pancakes. And what does that give me?
0.8.
Times 100, right?
Times 100 would be 8.
Gives me 80%. So 80% is the percentage yield. That's all it is. That's all these terms really are. So now you know what the limiting reactant is, you know what the percentage yield is, and you know what the theoretical yield is. That's all it is, really. And that's all we have for section 5. All right? I'm going to erase this. You need more time? Okay, let me know. All right. So let's go on to section 6. Now what we talk about is we talk a little bit more about we're going to deal with these new terms that we've learned. Limiting reactant, okay, theoretical yield, the percentage yield. But we're going to look at it from the point of view of the initial masses of the reactants. Okay? So we're going to use a chemical equation as an example. All right? We're going to use the following. We have 2Na, which is a solid, plus Cl2, and you know this chemical reaction. It is a combination or synthesis reaction. And what am I making? Making good old salt, right? Sodium combined with chlorine gas gives me NaCl salt. So I'm going to use that, and let's say in the laboratory, okay, I weigh out 52.2 grams of sodium. All right, that's one given. Now you're going to have another given. This is a problem with multiple givens. Now I'm also going to mess with 65.8 grams of Cl2, chlorine gas. Right? And what we're going to find is we're going to find the limiting reactant. And we're also going to find something else. We're going to find the theoretical yield. Okay? In order to do this, okay, you're going to need the following. You're going to need the molar mass of sodium, Na, which you find from the periodic table, Cl2, and the product, which is NaCl. When I say molar mass, you should know by now that that's the grams per mole that we normally get off the periodic table. So you go to the periodic table for sodium, chlorine, and sodium chloride, and you figure out what the grams per mole are for each one of these. And then you use your givens. Okay, we've got 52.2 grams of sodium. Then I'm going to use the grams per mole. 1 mole of sodium is 22.99 grams of sodium. And check me if I'm right. Make sure I'm right on this, so I'm doing it correctly. Now the grams of sodium are going to cancel just like we did last time, and I'm left with the moles of sodium. Okay? So now what I'm going to do is I'm going to get a relationship that involves moles of sodium in the denominator, and then I'm going to get the moles of sodium chloride, NaCl, in the numerator. Okay? Where am I going to get that relationship? I get it from the coefficients. Remember, there is a 2 here, there's an imaginary 1 here, and there is a 2 there. It all comes down to the coefficients. In your practice problems and in your homework, you might be given a chemical equation and you have to balance it. So this is where balancing the chemical equation is critical first. It's a critical first step because you're going to use the coefficients in these ratios. So I've got how many moles of sodium? I've got 2, right? So the 2 goes right there. How many moles of sodium chloride? I've got 2, all right? So my moles of sodium cancel with my moles of sodium, and I'm left with the moles of sodium chloride, okay? I'm not done yet because I have to get grams of sodium chloride. So what I need is I need a relationship between the moles of sodium chloride and the grams of sodium chloride. Well, that's the molar mass. That's what the molar mass is. I know that if I have 1 mole of sodium chloride that I've pre-calculated, I have 58.44 grams of sodium chloride. And check my math, make sure I'm right. Okay. And I've got moles of sodium chloride cancel, and I'm left with the answer, which is grams of sodium chloride. Now you do all the multiplication and division. 2 over 2 is 1, so that is nice and easy. So I've got 58.44 times 52.2 divided by 22.99. And when you do all that jazz, you should get, let's see, I get 135 grams of sodium chloride. Okay? Why am I doing all this? Remember, I have to find out what the limiting reactant is. Does this tell me what the limiting reactant is? No, because I've got two reactants, right? I've got sodium as one reactant, and I've got chlorine, which is the other reactant. So what do you think I'm going to do? I'm going to do the same process here for chlorine. All right, so I'll try to do it a little quick for you. I know it's not that exciting. So it turns out I've got 65.8 grams of Cl2, which is chlorine gas. That's the given that I'm given. All right. If I look up the molar mass of chlorine, I know that for every mole of Cl2, which is chlorine gas, that's going to be 70.90 grams of Cl2. From the chemical equation, I know that I've got a relationship between the moles of sodium chloride, NaCl, and moles of chlorine gas. And then I know I've also got a relationship, that same relationship for NaCl, 58.44 grams of NaCl divided by 1 mole of NaCl. Grams of Cl2 cancel with grams of Cl2, all right? Moles of chlorine gas cancel with moles of chlorine gas. Moles of sodium chloride cancels with moles of sodium chloride. And I'm left with so many grams of sodium chloride. All right? You do all the math on your calculator. I'm left with 108 grams of sodium chloride. All that to get the answer. So, have we found out what the limiting reactant is?
Yes.
Which one would you say it would be?
65.8.
Well, what is 65.8? The limiting reactant is chlorine. So the limiting reactant is chlorine because it produces the least amount of product. It yields the least amount of product. Have we found the theoretical yield?
No.
Why not? I think we have, right? What is the theoretical
It's
yield?
the amount that comes from the.
It's the amount that comes from the what? The limiting reactant. So this is the limiting reactant. What's the yield from the limiting reactant? The yield is 108 grams of sodium chloride. So you get a 2 for 1 out of this. All that work comes down to 2 answers, which is good. You get the limiting reactant is this, and you get the theoretical yield is that. The proper way to say the limiting reactant, you say the limiting reactant is chlorine gas, and you say the theoretical yield is 108 grams of, so when you give the theoretical yield, you have to give the amount, because you have to tell me how much. That's what the yield is, right? So, suppose we do a synthesis reaction. Now this is theoretical. What does theoretical mean? It means it's how it appears normally in the book. That's different than when you go upstairs in the lab, right?
Yeah.
When you go upstairs in the lab, sometimes different things happen, right? Why is that? Because some things, usually most of the time, things are a little bit different than what they are in the book. Why is that the case? Is chemistry wrong? No, not really. This is an oversimplified situation of what's really going on in the real world, okay? In the real world, okay, you'll have sodium and chlorine that combine that give you sodium chloride. But there's inefficiencies in your lab equipment. Maybe your sodium isn't pure sodium. Maybe you have some impurities in the sodium. There's no such thing as absolutely 100% pure substance of sodium. You could have 99.999% pure, and you can't have 100%. You're going to have some impurities in there. So what I'm getting at is that you might actually do this reaction in the lab, and you find out that your actual yield, the actual yield, is 86.4 grams of NaCl. The actual yield is 86.4 grams of Cl when you do this in the laboratory, okay, as opposed on the board. On the board, the theoretical yield was 108 grams of sodium chloride. Due to inefficiencies and impurities in the substances, what does this tell you? It tells you that you're never ever going to be able to produce the theoretical yield. You could get real close, you know, to 108 grams of sodium chloride. You might even get 107 maybe, but you'll almost never get 108, okay? Turns out in this experiment, you got 86.4 grams of sodium chloride. So what am I getting at? I'm getting at what the percentage yield is. The percentage yield, remember what the definition of percentage yield is? It's the actual, right, divided by the theoretical times 100%. So you put the 86.4, right? 86.4 divided by the 108, and you multiply it by 100%. And turns out, if my calculation is correct, you get 80%.
I'm sorry, just to cut you. Where did the 86.4 come from?
Okay. The 86.4 grams of sodium chloride is not anything that you're given or anything like that. This is a textbook example of what you would get when you add sodium and chlorine together, get sodium chloride. But when you go upstairs, right, when you do the lab with the nice lady upstairs, right, you might have a reaction where you have chlorine gas and sodium. And then you say, well, Professor Jim told us that you should get 108 grams of sodium chloride, you know, provided I've got 65.8 grams of chlorine gas. But it turns out when you did the lab, okay, you only got 86.4 grams of sodium chloride.
Okay.
That's because there's inefficiencies in the process, in the real world process. So this is kind of like an efficiency number. You're only 80% efficient, right? You're only getting 80% of what the theoretical is. Okay, and now we've got our last section. How are we doing on the video? Is knowing terminology and nomenclature and knowing what these things are. And the math isn't really that bad, because in chemistry, the most math that you're ever going to do is algebra. You're never going to use calculus. You're never going to use trigonometry or geometry. The worst that you're going to do is using algebra. Okay, section 7 is about enthalpy. Enthalpy, yeah. What is enthalpy? Okay, well, it's a measure of the heat evolved or absorbed in a reaction. That's all it is. That's what enthalpy is. Now, chemical equations can be classified as two different things when we're talking about heat. We can say, okay, so in reference to a chemical reaction, they can be exothermic or endothermic. So exothermic, what that means is it releases heat. I have a chemical reaction that takes place and it releases heat. I have the reactants on the left-hand side and the products on the right-hand side. When I bring the reactants together, just like sodium chloride, right? Remember that video I showed you? When I bring sodium and chlorine gas together, what happens? There's a yellowish type of light that goes off, and there's heat and there's light that comes out of this reaction. That's an excellent example of an exothermic reaction. It produces heat, produces energy. Not all reactions are like that. There are some reactions that are endothermic, and what that is just the opposite. I bring the reactants together, and they'll absorb energy. You might not see anything going on, but maybe the temperature will go up in the products. So if you have a thermometer on the situation, you can see the temperature has risen, so you can see something happen. So what happened was not only are the reactants coming together, but there's also energy going into this. So the product has got your reactants that have combined plus energy, okay? All right, so we give this enthalpy of reaction a certain symbology. And the symbology we use is as follows. This is the Greek letter delta, H, and RXN. Okay? Let me explain what this means. Whenever you use the Greek letter delta, uppercase delta, whenever you use that uppercase delta, that always means a change. Okay? That means I have an initial state and a final state. So this delta means something changed. Whenever I use the letter H, the capital letter H, you'll see it in a lot of other books on chemistry and as well as physics. H always represents the energy due to heat. Energy takes on many, many different forms. One of the forms it takes on is heat. So what is this RXN all about? All that is just shorthand for saying reaction. That's all it is. RXN is reaction. It's not R times N, it's reaction. So what this is the enthalpy of the reaction, which is the change in the heat of the reaction is what the enthalpy is. Okay? Now there are certain rules about this symbol. Delta H RXN, okay? For exothermic, remember exothermic is when it releases heat, is negative. So if I have a negative result for the delta H RXN, it means I have an exothermic reaction. Okay? The delta H RXN for endothermic is positive. There you go. Negative, positive. Okay. So those are some concepts that you need to know about this stuff. All right. Now let's pick on another chemical reaction. All right. Let's pick a chemical reaction of C3H8. Okay. Plus 5 O2s gives me 3 carbon dioxides plus 4 H2O. And I'm given another bit of information. You have to be given this, okay? In the reaction, I'm told that the delta H RXN is equal to negative 2,044 kilojoules, all right?
How is that reaction followed?
The joules of that.
What's that?
How is that followed?
How is that? Oh, you have to, like I said, you have to be given this. You have to be given this.
Okay.
So you're not going to be expected, oh, it's, you know.
I'm just wondering how they got it, that's what I'm asking.
Oh, okay. Oh, how did they get it in the laboratory? That's a great question. So there's an experiment called bomb calorimeter, okay, that I did when I was an undergraduate. And it's a closed container. You can take minute amounts of sample. You don't take large amounts for obvious reasons. But you take small amounts of sample and they react. And there's a small, tiny little explosion, little, you know, not even a firecracker, that takes place inside of the calorimeter, which is an enclosed, thermally isolated thing. It's got a thermometer that's stuck down next to the reaction. And one way of measuring, there's a relationship between the amount of heat energy and temperature. There's a linear relationship between heat and temperature. And from that, I can extrapolate how many joules of energy comes out of the chemical reaction. Yeah, it's a good question. So obviously someone did this in the lab, right? And they measured this. You know, they measured that the enthalpy of reaction, they measured negative 2,044 kilojoules. Now, what is his question? What's a joule? A joule is a unit of energy, and it's spelled like this, okay? 1 joule, Joule, okay? Named after James Joule, okay? Who messed around with this stuff. So 1 joule is a unit of energy. It can be used for not just heat, but it can be used for mechanical energy. It can be used for electrical energy even, okay? 1 joule is a unit of energy, okay? Maybe if you learn physics, or if you take a physics course, you'll learn the basic definition of work. Work is force times distance, okay? So another way of looking at what a joule is, work has units of joules. A joule is equal to 1 Newton times a meter. So it's the force of 1 Newton over the distance of 1 meter gives you 1 joule of energy, okay? So that's, I'm not going to expect you to know that for this course. But since he asked, that's where a joule comes from. A joule is a unit of energy. Now, a kilojoule is 1,000 of those. So